Hello friends, welcome to Engineering Funda family. In this video, I will explain Duobinary signaling with great clarity. Before I start with my explanation, let me tell you the outlines of this video. In this video, first of all, I will discuss about basics of Duobinary signaling. After that, I will explain Duobinary encoder and Duobinary decoder without precoder. If you don't use precoder, then there will be issue of error propagation. So after that, I will use precoder in encoder and decoder to resolve issue of error propagation. At last, I will explain transfer function and frequency response of duobinary conversion filter. So here I will explain encoding and decoding process along with examples. And at last, I will explain transfer function and frequency response of duobinary signaling. So let us start this video with first agenda, that is basics of duobinary signaling. See, duobinary signaling is also known as correlative coding. In duobinary signaling, what we do is we correlate current bit with previous bit. In duobinary signaling, simply we will be adding current bit with previous bit. That's why it is also known as correlative coding. Here we are performing correlation of current bit with previous bit, right? It is also known as partial response signaling. See, in normal response signaling, if you have bandwidth W, then maximum data rate will be W bits per second. But in partial response signaling, you can achieve higher data rate compared to bandwidth. So here in duobinary signaling, if you have bandwidth W hertz, then data rate can be 2W bits per second. That's why it is also known as partial response signaling. In duobinary signaling, we will be introducing controlled ISI, and that we introduce intentionally by adding current bit with previous bit. In duobinary signaling, if you have current bit that is B of k and 1 bit delayed signal that is B of k minus 1, then duobinary output will be B of k plus B of k minus 1. So here what we do? We add current bit with previous bit. But remember one thing, see here our binary signal that will be polar signal. Means for logic 1 we will be having plus voltage and for logic 0 we will be having minus voltage, right? And see this polar binary signal B of k and 1 bit delayed signal that is B of k minus 1 that we are adding, that is duobinary output. Means here we are performing correlation of 2 bits, current bit with previous bit, right? See, this correlation of current bit with previous bit introduces controlled ISI, right? And here in duobinary signaling, we can achieve signal rate of 2B0 bits per second with the bandwidth of B0 hertz, which is way better than Nyquist rate. The reason is Nyquist filter is not practically realizable as it is sharp edge filter, right? And using duobinary signaling, one can achieve double of the data rate with the bandwidth B0, right? That's why name is DU. So DU means doubling the transmission capacity, right? So how we can have 2B0 bits per second data rate along with the bandwidth of B0, that I'll explain along with transfer function and frequency response. And here I will also solve problems based on encoding and decoding. So that will gives you more clarity. So now let me explain encoding process. Remember, see this encoding process that I will explain without precoder first. So without precoder, encoding is very simple. See here we have polar binary signal B of k and that we give it to 1 bit delay. So here we have signal B of k minus 1. Simply we are giving these 2 bits to adder. So addition is C of k is equals to B of k plus B of k minus 1. And this signal that we pass it through ideal filter. this ideal filter is Nyquist filter. Practically, one cannot implement this. See, practically one cannot have sharp edge filter like this. But if you use Duobinary encoder along with this filter, then it is possible. That even I'll explain along with transfer function and frequency response. Right now consider, even if you don't have ideal filter over here, still you will be having band limited Duobinary output, right? And this output will be how much? C of k is equals to B of k plus B of k minus 1, right? See here, this input signal, that is polar binary signal. What it means? It means for logic 1, we will be having plus 1 voltage. For logic 0, we will be having minus 1 voltage, right? This B of k, that we give it to adder along with 1 bit delay, right? So here, output of adder, that will be C of k, that is B of k plus B of k minus 1. See this C of k, that is addition of B of k and B of k minus 1. So possible output will be plus 2, 0 and minus 2. See, if you have same polarity like logic 1, logic 1. For logic 1, we have plus 1 voltage. So 1 plus 1, that will be 2 volt. If you have opposite polarity means 0, 1, then for 0, we have minus 1 and for 1, we have plus 1. So plus 1 minus 1, that will be making 0 voltage over here. And if you have logic 0, then minus 1 voltage, that is getting added and it is resulting into minus 2 voltage. So after adder with C of k at output side, we will be having plus 2, minus 2 and 0 voltage, right? See, practically this ideal filter cannot be realized, but if you implement this filter along with Duobinary encoder, then that is possible. Now let me explain one example. So here, what I'll do is I'll consider one binary data, that is 0, 0, 1, 0, 1, 1, 0. See, this is binary data. Now we need to represent that in form of polar binary B of k. With polar, logic 1 is there with plus 1 voltage, logic 0 is there with minus 1 voltage. So B of k, that will be having minus 1 voltage for logic 0 and plus 1 voltage for logic 1, right? You can observe it over here. Now let me explain B of k minus 1. That is 1 bit delayed signal, right? So now see B of k minus 1, that is 1 bit delayed signal. So question is, what should be first bit? So that we are assuming. And condition for assumption is it should be same as B of k. So this first bit, that is minus 1 over here. Why? The reason is here with B of k we have minus 1, right? And see this B of k minus 1, that is 1 bit delayed, means this minus 1 will come here, this minus 1 will come here, this plus 1 will come here, this minus 1 will come here, this plus 1 will come here and this plus 1 will come here, right? So that is how we have B of k and B of k minus 1. First bit, that should be assumed and that should be same as B of k, right? Now simply we give it to adder. So now we need to perform addition, that is C of k. So addition is minus 1 minus 1 minus 2, minus 1 minus 1 minus 2, plus 1 minus 1 0, minus 1 plus 1 0, plus 1 minus 1 0, plus 1 plus 1 2 and minus 1 plus 1 0. And this is what we will be transmitting, that is band limited Duobinary output, right? And this Duobinary output, that we give it to decoder. So let me explain decoder. See, decoder is quite simple. This Duobinary signal, that we give it to switch. This switch is getting pressed over here at TB interval. So here we have C of k, right? And this C of k, that we give it to decision device, and decision device, that will gives you binary signal over here. Here you need to understand how decision is taken. See, decision, that is based on plus 2, minus 2 and 0 voltage. This C of k, that can be having plus 2, minus 2 or 0 voltage, right? If it is plus 2, output is bit 1. If it is minus 2, output is bit 0. And if it is 0 voltage, then output will be complement of previous bit. So this is what decision device condition. right? And based on this condition, one can decode binary signal. So with encoder, I have considered this case, right? Binary data was 0010110, and I have told you C of k, that is this, right? Now here if you apply this decision device, then see with -2 there will be 0. With 0 there should be complement of previous bit, and with +2 there will be logic 1. So if you observe decoder output over here, so with -2 0, with -2 0, with 0 complement, so 0 to 1, with 0 complement, so 1 to 0, with 0 complement, so 0 to 1, with +2 there will be +1, with 0 there will be complement, so 1 to 0. If you observe this decoder data, so that is same as binary data, right? So we have successfully decoded it over here using Duobinary decoder. But with this Duobinary encoding and decoding process, there is one issue. Let me explain that. See here, there can be issue of error propagation. Let me take one example. Here, let us assume we have this C of k, and with this C of k, with second bit, we have error. Let us assume due to some channel noise, there is error in second bit. And at decoder side, we need to identify ones and zeros. So if you observe, see decoder data. So here with -2, we have logic 0. Here we have 0. So with 0, complement 0, so 1. Now again 0, so complement 1, that is 0. Here we have 0, so complement 0, here we have 1. Here we have 0 voltage, so complement 1, here we have 0. Here we have +2, so +2 is having logic 1. Here we have 0, so complement 1, we have 0, right? So if you observe with second bit, we have error. So but obviously this is having error. But due to complement process with 0 voltage, here error is propagated, right? So even though you have a single bit error, there is error propagation. So that is the issue. And this issue that can be resolved using differential encoder, that is referred as precoder. So now what I'll do is I'll be explaining Duobinary encoding process along with differential encoder, that is referred as precoder, right? So if you observe the block diagram, then see this much portion is same, right? Only we are adding precoder. Now you need to understand this precoder. See here we have binary signal that we give it to XOR gate, and in feedback 1 bit delayed signal is given. So if I say XOR output is A of k, then 1 bit delayed signal over here is AK minus 1, right? So A of k is XOR of B of k and AK minus 1. And here, see this A of k that we give it to NRZ polar, means here we have polar signal. And now we do same process as we have done it without precoder. We will be adding A of k and A of k minus 1, that is C of k. Then we pass it through ideal filter and we have band limited duobinary output, right? So here with this XOR gate, output is A of k, that is B of k XOR with A of k minus 1. And that we give it to NRZ polar. With polar signal, one should know with logic 1, we have +1 voltage. With logic 0, we have -1 voltage, right? See, without precoder, I have explained that A of k minus 1, that should be assumed with first bit, and that has to be same as B of k. But with precoder, you don't need to assume A of k minus 1. You can assume first bit with any value. It can be selected as logic 0 or logic 1, right? Now let me explain this encoding process along with precoder by one example. So here, first of all, I'll consider binary data, that is 00, 10, 110. So that is B of k, right? And here we will be having A of k, that is XOR operation of B of k and A of k minus 1. So first of all, first bit of A of k minus 1 that we need to assume. So here A of k minus 1 that we have assumed with logic 0. You can assume that by logic 1. There is no issue with that. Now see, B of k and A of k minus 1 that we need to XOR, that is A of k, right? So 0 XOR 0 means 0. And then this 0 that is getting shifted over here means here we have A of k minus 1. So 0 is coming here. Then 0 XOR 0, that is 0. This 0 is coming here. 1 XOR 0, that is 1. This 1 is coming here. 0 XOR 1, that is 1. This 1 is coming here. 1 XOR 1, 0. This 0 is coming here. 1 XOR 0, that is 1. And this 1 is coming here. 0 XOR 1, that is 1. So that is how we have A of k after XOR operation, right? Now that is what we give it to NRZ polar. So NRZ polar, that will be converting logic 1 with plus 1 voltage and logic 0 with minus 1 voltage, right? So now we have A of k and A of k minus 1 along with values. You can observe A of k and A of k minus 1 in terms of logic 0 and logic 1 is there with us. And in terms of voltage, here for logic 0 I have placed minus 1 and for logic 1 I have placed plus 1, right? Now this C of k, that is simply addition of A of k and A of k minus 1. So C of k, that will be minus 1 minus 1 minus 2, minus 1 minus 1 minus 2, minus 1 plus 1 0, plus 1 plus 1 2, plus 1 minus 1 0, minus 1 plus 1 0 and plus 1 plus 1 2. So this C of k, now that we are passing it through ideal filter and we have band limited Duobinary output, right? So here we have used precoder using XOR gate, right? Now let me explain decoding process. See, decoding process is quite simple. This Duobinary signal that we pass it through this switch, that is getting turned on after TB duration, and here we have C of k. This C of k is given to decision device, and this decision device that will generate binary data. So here you need to understand decision conditions. See, with this C of k, there can be plus 2, minus 2 or 0 voltage, right? See, if you have plus or minus 2 voltage, then output should be logic 0. And if you have 0 voltage, then output is logic 1. Simply that is how this decision device is taking decision. And this is what the decision condition which we have it with precoder, right? Without precoder, I have told you decision conditions were different. Without precoder, decision conditions were logic 1 for plus 2, logic 0 for minus 2, and with voltage 0, we have complement of previous bit. But as if we have precoder, then decision condition, that is logic 0 for plus or minus 2, means if you have same polarity with current bit and previous bit, then there can be plus or minus 2. In that case, output bit will be 0. And if you have opposite polarity with current and previous bit, so that is resulting into 0 voltage. At that time, output will be bit 1, right? So here I have done that encoding process with my previous slide, and we were been transmitting this signal, right, as per this binary data. Now this C of k, that is given to decision device. Here this decision device that will take output as a logic 0 if plus or minus 2 voltage is there, and it will give logic 1 if output is 0 voltage. So here if you observe binary signal, so for plus or minus 2, here we have logic 0, and for 0 voltage we have logic 1. And if you observe this decoder data, then this is same as binary data. You can observe both are same. So here we have done successful implementation of Duobinary decoder and encoder along with precoder, right? Now here one thing that you need to understand. See, without precoder, we were been doing complement as if C of k is 0 voltage, right? But here with precoder, we don't perform complement process. As we don't perform complement process, there won't be any propagation error, right? So for 0 voltage, here we don't perform complement of previous bit. So there cannot be any error propagation if you use precoder. And in precoder, we were been using one XOR gate, right? Now let me explain transfer function. To understand transfer function, one should know what is Duobinary encoder. See, in Duobinary encoder, first of all, we perform addition of current bit with previous bit. Here current bit is B of k and previous bit is B of k minus 1. So Duobinary encoder adds current bit with previous bit. After that, we pass this signal through ideal Nyquist filter. And then we have Duobinary output. So here we have cascaded form of Duobinary encoder with ideal Nyquist filter. So first of all, let me explain transfer function of Duobinary encoder. Here we have input signal that is B of k. So first of all, we need to identify transfer function of input signal. So transfer function of B of k, that is B of f. So what will be transfer function of B of k minus 1? That will be B of f into e to the power minus j 2 pi f tb. This is what we have it based on property of Fourier transform. If you have 1 bit delay, then transfer function will be B of f into e to the power minus j 2 pi f tb, right? Now I'll explain you transfer function of Duobinary encoder, that is Fourier transform of output divided by Fourier transform of input, right? So Fourier transform of B of k plus B of k minus 1 divided by Fourier transform of B of k. So B of k is having B of f and B of k minus 1, that is having Fourier transform of B of f into e to the power minus j 2 pi f tb. So here this B of f, that is getting cancelled and we have 1 plus e to the power minus j 2 pi f tb. Now see, from this, if you take e to the power minus j pi f tb common, then here along with 1 we will be having e to the power j pi f tb. And this is what one can represent in form of cosine. So one should know cos of pi f tb, that is e to the power j pi f tb plus e to the power minus j pi f tb divided by 2. So 2 cos pi f tb, that is this. And if you take magnitude, then this e to the power term, that is getting unity. So this is the magnitude of Duobinary encoder h of f, right? And if you talk about transfer function of ideal Nyquist filter, then that will be T of B, where bandwidth is there from minus FB by 2 to plus FB by 2. That will be simply rectangular function, right? That will be rectangular function. Rectangular function means here amplitude will be TB and there will be sharp edges at minus FB by 2 to plus FB by 2. So here, see what will be overall transfer function. Overall transfer function, that will be cascaded form of this two, means multiplication of this two. So if I say overall transfer function is HD of S, then that will be multiplication of this two. So that is 2TB into cos of pi f TB, where this frequency f, that is ranging from minus FB by 2 to plus FB by 2, right? Now let me show it to you in terms of frequency response. So you can observe this is cosine function, where this cosine function, that is having maximum amplitude 2TB, you can observe. And frequency is ranging from minus FB by 2 to plus FB by 2, right? So here, see with ideal Nyquist filter, we have sharp edges like this, right? But if you observe combination of Duobinary encoder with Nyquist filter, then we don't have sharp edges over here. So practically one can implement this. With this response, if you observe bandwidth, so that is simply FB by 2. And it is practical. It is not sharp edge. It is practical filter. And maximum amplitude is 2 TB. Right. So this duobinary encoder and decoder, that can be implemented practically, and by which one can achieve bandwidth of data rate that is twice of the bandwidth of message frequency. Right. So here we have partial response signaling. Why? The reason is here we are achieving higher bandwidth. With Nyquist filter, you should be having data rate that should be lower compared to this. If you have W bandwidth, then with Nyquist filter, you can transmit data rate as per W bits per second. But with duobinary signaling, if you have W bandwidth, then you can transmit 2W bits per second data rate. So that is the advantage of this. The reason is it is practical, and here we are performing correlation of current bit with previous bit, where we have controlled ISI, due to which one can have higher data rate transmission. I hope you have enjoyed this session. Still, if you have any confusion, just place that in comment section. I'll be happy to help you. Thank you so much for watching this video.